It gives me happiness and pleasure in presenting what little I know amongst you today. My Before I start, my special thanks to our head of the department, Professor R. Venkatramanan, who trusted me in presenting this and gave an opportunity. So I will be talking about on some open problems in mathematics. This topic is somewhat different from others. See, there were 14 talks in this FDP, and I think almost all the rest of the talks were focused on key aspects. Like they have given some special topic on this, but I am probably the only person to have been presenting in a special, uh, different idea, not mainly focused on a particular uh, concept, but for presenting some open problems on emerging on different areas of mathematics. So I hope this ideas will stimulate young faculty, at least some of the faculty who are working and who join newly into teaching profession, to get some motivation and work out in future. So with this short introduction, I shall begin my presentation here. So is the screen visible? Hello?
Yeah, visible, visible. Yeah, visible.
Okay. So I will begin with probably 2 millennium old problem. See, the problems which are not unsolved but seems to be true are called conjectures. So conjecture is the name for problems which are not resolved so far, but it remains to be true upon verification. So I begin with twin prime conjecture, which means, see, primes are very special numbers. Among galaxy of number that we have in our counting system, prime numbers occupy a very special place. And among prime numbers, there is a special mention about what is called twin primes. Now, this portrait here of Euclid was considered to be the one who compiled the first book on mathematics, and he mentioned about prime numbers in his ninth volume of the most famous book called Elements. And in that Elements book, he proved that there are infinitely many primes, which was considered to be one of the very classic proof. See, if you want to have a look at a very good proof, you have to look at that particular proof by Euclid, which was a very wonderful proof. We take assume that the contradiction, that there are only finitely many primes, take the product and add one to it, you arrive at a contradiction. Therefore, by proof of contradiction, you can prove that there are infinitely many primes. This is a short gist of how Euclid showed that there are infinitely many primes. Now, coming to twin primes, now Euclid proved that there are infinitely many primes some 2,300 years ago, not now. So it was very, very early time. Now, since then, people were guessing that there are infinitely many twin primes also. What is a twin prime? The twin primes, pair of primes with two difference between them. Like prime numbers of the form p comma p plus 2. Any pair of the form p comma p plus 2, for where p is a prime number, is called a twin prime. Simply speaking, numbers like 3 comma 5, 5 comma 7, 11 comma 13, 17 comma 19, 29 comma 31. These numbers are twin primes, which are showed here. And if you list down those list of twin primes, you see these are all multiples of 6. And twin primes either will look like multiple of 6 minus 1 and multiple of 6 plus 1. So of course, 3 comma 5 is an exception to this rule. So any pair of twin prime will look like multiple of 6 minus 1 and multiple of 6 plus 1. The rest of all except 3 comma 5, the first pair of twin prime, all the other twin primes will either belong to, the first one will belong to this category, like multiple of 6 minus 1, and second category in the pair will belong to multiple of 6 plus 1. So either it is 6n minus 1 or 6n plus 1 or something like that. Okay. So it aligns very neatly. You have some pattern for twin primes. But unfortunately, even observing this pattern, mathematicians for over 2 millennia could not show that there are infinitely many primes. This is one of the oldest unsolved problems that exist. To go with another oldest unsolved problem, like existence of odd perfect numbers. So I have spoken in brief about perfect numbers in my webinar before. So there exist. I mean, people cannot find odd perfect number as of now. but they believe such a number would exist, and if it exists, it's a huge number. That is all we know, but no one has come up with an existence of odd perfect number. Now, what happened is twin primes are numbers of the form multiples of 6 minus 1 multiple of 6 plus 1, except the first twin prime, which is 3 comma 5. In general, twin primes differ by 2 between them. Pair of primes differing by 2 are called twin primes. Okay, so those twin primes are marked with blue color here, as you can see. So 23, of course, 23 plus 2 is 25. 25 is not a prime number, it's a composite number, so this doesn't form a twin prime. Whereas 29 comma 31 is a twin prime, 41 comma 43. Just like there are infinitely many prime numbers, right from Euclid's period, people believe that there are infinitely many twin primes, but unfortunately, no proof has been given till today. This is one of unsolved problem that remains in mathematicians' field. Now listen, I observed this property that if you take set of integers modulo 6, which is from 0 to 5, that these are all class of numbers which are divisible by 6. These are all class of numbers which gives remainder 1 upon dividing by 6 up to 5. Because if you divide any number by 6, the maximum possible remainder is 5. So this 5 will be class of all numbers which are divisible when divided by 6 gives remainder 5. Okay, so this is Z6, and we know that Z6 comma plus 6 under addition modulo 6, this forms a cyclic group. And interestingly, you find for this particular cyclic group, the elements 1 and 5 will form the generators for this particular cyclic group. This I observed myself. And if you look at this table here, these are all numbers which are 6r plus 5. I mean, these are all numbers which gives remainder 5 upon dividing by 6. And these are all numbers which gives remainder 1 upon dividing by 6. And these numbers are precisely 1 and 5 here. So this twin primes form generator for cyclic group of 6 elements. They are generators, and inverse of 1 is 5 and inverse of 5 is 1. So they form a good pattern even in cyclic groups, not only in numbers. Okay. Now, as I mentioned, pair of the numbers of the form p comma p plus 2 for p prime number is called twin prime. Twin prime conjecture says that there are infinitely many twin primes. In fact, a mathematician called Polignac extended this idea, and he conjectured that there are infinitely many primes of the form p comma p plus 2k. And if k is 1, you get twin prime conjecture. So primes which differ by 4, for example, primes which differ by 6, primes which differ by 8. So primes which differ by some even number of the form 2k. Now he conjectured that there are infinitely many primes of the form p comma p plus 2k, and that general conjecture is called Polignac conjecture. Now several mathematicians right from ancient time to modern time were vigorously working on resolving this twin prime conjecture, but unfortunately not very good improvement was shown until 2013, when Yitang Zhang, American mathematician, proved that limit infimum of Pn plus 1 minus Pn is less than n. That means this result conveys the fact that there are infinitely many primes whose difference is less than 70 million, 7 followed by 7 zeros. So he showed that there are infinitely many twin primes less than n, where n is 70 million. This upper bound for difference of primes is too high, I mean, in terms of numbers, and therefore people started working in the project called Polymath project, and James Maynard and Terence Stone. James Maynard is a young mathematician who got Sastra Ramanujan Prize for his work on twin prime conjecture. And Terence Stone needs no introduction. He is one of the best living mathematicians as of today. He is a Fields medalist from the year 2006, and he is one of best mathematicians to be living as of now. So these two people involving in Polymath project reduced this upper bound given by Zhang from 70 million to 246. Of course, using this particular idea, like Elliott, Halberstam conjecture, they could even reduce this 246 bound to 12,6. But this remains as a conjecture. So far we can't take this as a guaranteed. If this conjecture fails, then this bound will be false. But anyway, we now know that there are infinitely many primes of difference up to 246. Now we have to try to bring this down, and once this bound comes to 2, we are through. We will be proving twin prime conjecture, that there are infinitely many primes which differ by 2. So this is what the current state is, and these three people are very important for making big breakthroughs in the recent times, right from for the last 6 or 7 years. Zhang is here, James Minot, and Terence Tao. Now, twin prime conjecture, of course, is verified by computer up to 4 quadrillion places, 4 into 10 power 18 places. So that much numbers were verified, and when people worked on computers, they verified up to 4 quadrillion places. There are, in fact, twin primes, but still that is not sufficient for proving that there are infinitely many primes. Coming to the second most important, see, this list is not exhaustive, but these are all problems which I liked to my mind. Of course, there are preferences for every person, and these problems were somewhat easier to state for the general audience, but because there are some open problems that were very, very hard to even understand. So I rejected such problems. I was collecting problems which are quite easy to understand, comprehend, and then probably give an idea of how far it has been solved now and who has trying to solve them and what is the current status of the problem. Somewhat good thing that you can understand, because there are some problems which are very hard to even understand the given statement, and therefore it is difficult for us to think about it later. Now, um, Goldbach conjecture was named after Goldbach, who wrote a letter in 1742 to the most important mathematician called Euler. Of course, Euler is even today considered to be the most greatest among all uh, mathematicians ever lived on this planet. Okay, Leonhard Euler is considered to be the master of everyone. Okay, now. Um, he wrote a letter, and then he said some statement which was probably assuming that 1 is a prime number. Goldbach assumed that 1 is a prime number, and he wrote some observation here, you can see it here. So he decomposed any number by 1 also. So 1, of course, is not prime in modern area. In those times, some mathematicians took 1 as a prime number. Okay. Then Euler immediately corrected it and resent a letter to Goldbach stating this theorem. So this was refined by Euler, not the original statement by Goldbach. Euler said that your statement should be redefined like this, and he said that every even integer greater than 2 is sum of 2 primes. So of course 2 you cannot write a sum of 2 prime, because 2 is the least prime number. Therefore, there's no possibility of decomposing 2 into smaller primes. So, but you can write 4 as 2 plus 2. You can write 6, for example, as 3 plus 3. So, every even number greater than 2 is sum of 2 primes. Those 2 primes need not be distinct. They can be equal, like 3 plus 3 or 2 plus 2 or something. Okay. And the other conjecture that Euler got from Goldbach writings is this: every odd integer greater than 5 is a sum of 3 primes. As you can easily verify, like if you take 7, for example, you can write it as 2 plus 2 plus 3. Okay, if you take 9, you can decompose it. This is a very easy task actually. 9 is 3 plus 3 plus 3, sum of 3 primes. So it may not be distinct. The number that you take may not be distinct, of course. Now, this is called strong conjecture, and this is called weak conjecture, because if one proves strong conjecture implies weak conjecture. That means if I can show that every even integer greater than 2 sum of 2 primes, then that will immediately prove that every odd integer greater than 5 is sum of 3 primes. This will follow, weak conjecture will follow from strong conjecture. Now, people were trying to solve both of these conjectures, and this is again around 280 years old as of now, because this was, as I told you, conjectured in the year 1742. So we are 279 years right from the year when it was first proposed. Now, if you take these numbers here, you can see this is a pictorial representation of Goldbach's strong conjecture. Some may refer this because the sum of 2 prime, this is called Goldbach binary conjecture, binary for 2. And the second weak conjecture is also termed as Goldbach ternary conjecture because of 3. So this is sometimes called ternary conjecture. This is sometimes called binary conjecture. Okay. So if you take the binary conjecture, this is a pictorial representation like 4. See, we have written primes on either side of this number triangle. 4 is 2 plus 2. So intersection of 4 lies in the intersection of 2 and 2. So So this dot here. So 4 is 2 plus 2. You can see 6, every even number greater than 2, which means 4, 6, 8, 10. Okay. So 6 is actually 3 plus 3. So 6 lies in the intersection of this 3 as well as this 3. Whereas if you take 8, 8 lies in the intersection of 3 and 5. So 5 is here and 3 is here. So only one way you can write 8 as sum of 2 primes. Whereas these two dots indicate that you can write 10 as sum of 2 primes in two ways. One way is 5 plus 5. So this 5 is here, this 5 is here, 5 plus 5. The other way is 7 plus 3 or 3 plus 7, whatever. So these two dots indicate that you can write 10 as sum of 2 primes in two possible ways. But you can write 12 in only one possible way, which is sum of 5 and 7. Sum of 2 primes, that is Goldbach conjecture. Whereas you can write 14 as sum of 2 ways. But the problem with, I mean, it's easy to see how things work in numbers of smaller magnitude. But if you take larger numbers with somewhat bigger magnitude, you see there are quite a number of ways. For example, 42 can be written as sum of 2 primes in 4 possible ways. And if we take 48, it has 5 different representations as sum of 2 primes. And therefore, since some of representations become more for larger numbers, it is quite difficult for mathematicians to comprehend and improving as much as possible. But thanks to some people who had been working on this tirelessly, we know something about it, which I will share with you. In fact, the people believe that the weak conjecture or ternary conjecture had been proved recently. This is a very recent proof. It was, you can see the paper, this paper, the ternary conjecture, Goldbach conjecture is true. This was published in the year 2014. You can look out for the paper in this link. Okay. It is available in the archive.org, which is collection of many good papers in mathematics. This is a source for many mathematical papers. Okay. Now, the ternary Goldbach conjecture is true. It was proved by this proof was given by Helf God, but some people, very few of them, still got doubt in it, and it was not, though it was accepted and published, it was not published in the main journal or annals of mathematics, because some people still suspect something in it. But most probably, very widely, it was believed that the weak conjecture has been proved by Helf God. It was seen as one of great breakthroughs in this century. Now, the next thing, that is Beal's conjecture. See, of course, to explain Beal's conjecture, we have to know a bit about Fermat's conjecture, like Fermat's last theorem in particular. This French mathematician Pierre de Fermat wrote this marginal note, which is in Latin term, cubum autumn in divos cubos and other things in Latin, which means that it is impossible to separate a cube into two cubes. That is, it is not possible for us to write a cube number as sum of two cubes or a fourth power number as sum of two fourth powers. In general, any higher power more than 2 can be written as a similar two powers. Like you can't write a power k as sum of b power k plus c power k when a, b, c are integers, whenever k is greater than 2, or a power n plus b power n is not equal to, or x power n plus y power n is not equal to z power n whenever n is greater than 2. Of course, this restriction is simply given because when n is 2, you have infinitely many triples like x, y, z satisfying, and that those triples are called Pythagorean triples, because we have many this equation to be true whenever n is 2, because we know that 3 square plus 4 square is 5 square, 5 square plus 12 square is 13 square. So whenever n is 2, you get your usual Pythagorean triple, but there are no triples x, y, z for which they satisfy this whenever, of course, x, y, z are integers. If they're non-integers, of course, we can find a solution, but when assuming that x, y, z are integers, and this was called, very famously called Fermat's last theorem, and this mischievous Fermat could have written the last line here, like Hans Marillinis executus non corpet, which means I have discovered a truly marvelous proof of this assertion, which this margin is too narrow to contain. I know the proof, but unfortunately, this margin, which I'm writing this note, marginal note, is too narrow to contain. So people got excited after seeing this marginal note by Fermat. This marginal note of Fermat became one of classic lines in the history of mathematics ever since it was written in 1637. And finally, due to the efforts of several mathematicians, ending with Andrew Wiles, this got proved in the year 1994 when a small error was rectified at that time. Then Andrew Wiles worked with the student Richard Taylor to rectify the small error, and finally the proof was accepted in the year 1995. So Fermat's last theorem has been proved now. That is one of the big theorem that has been proved in the last century. Okay. Now this man, Andrew Beale, this man named Beale was a notorious mathematician. He was mainly a businessman whom profile when I checked in the internet, he was one of the billionaires in America, and in Forbes list he comes around 67th place in the billionaires list in America as of now. So he owns nearly 8 billion US dollars of company. He runs a big bank, so that's called Beale Bank in his name. And this businessman, interestingly, posed a conjecture, which was considered to be more generalized case of Fermat's last theorem. Like he said that this is the main statement that he proposed, and this is given for better understanding. These two are equal actually. The equation a power x plus b power y is c power, that is sum of x power of an integer plus y power of integer cannot be equal to the z power of an integer. So the difference between Fermat's last theorem and this theorem, they're one and same. Looking at this x, y, z are replaced by a, b, c, but in Fermat's last theorem, you have same equal powers, like powers, all raised to the same power, but here the powers are different. What Beale said was, even Fermat's last theorem can be extended not only to like powers, it is also true for unlike powers, like one to the x power, the other to the y power, the other to the z power. The powers are different, and if they are at least three, then this equation has no solution. Mathematicians, with the help of supercomputers and programming skills, were working uh, for many years to identify such a, and he offered some prize also in 1997 for anyone who come across this. At that time, it was around $5,000, and he said that as years pass by, for every year of passing, the prize money will increase by 5,000 US dollars subsequently, and until 2010, when American Mathematical Society deposited the amount. Now the current status of prize money is 1 million US dollars, which was kept by AMS, and the interest of that amount until it was claimed was used for Erdős Memorial Lecture. So I will talk about Erdős little later. Okay. So people were trying to come up with this kind of equations, but unfortunately, one of the powers is at least two, not more than two. Beale's conjecture says that all this power number, that the exponents should be at least three, not two. But so far, whatever example that they have found contains at least one power of two here. At least a square has come here, and more than two, you can't find this. So Beale's conjecture seems to be true, but no one has proved it so far. So this is another example that you need not require great skills for making a good guess like conjectures like this, because Beale is not technically a mathematician. He was an amateur mathematician. So this notice was given by American Mathematical Society website and other things that I said now. Okay. So the prize money is, as I told you, is 1 million US dollars. So those who can prove Beale's conjecture is still open now. If you can prove it, it is well and good. You become instantly famous, and not only that, you can claim 1 million US dollars prize money. And Collat's conjecture is one of my very favorite open problem. I always present this everywhere. And this man is Collat, who made this conjecture in the year probably 1936 or 37, if I remember correctly, 1930s. He said that you take a number, natural number. If it's even, you divide it by 2. If it is odd, you multiply by 3 and add 1 to it. Keep on doing this. Ultimately, you will end up with the cycle 4 to 1. This is what you end up with. So for example, when you start with 10, 10 is an even number. Because it's even number, you have to divide by 2. So 10 divided by 2 is 5. Because it's odd number, if the answer is an odd number, use this formula. The answer is an even number, use this formula. So same function defined in two parities. If the number is odd, you use this rule. If the number is even, use this rule. 5 is an odd number, so 3 times pi is 15 added to 1, 3n plus 1. This is n for me. So 3 times pi is 15, added to 1 is become 16. This is an even number, so I divide by 2 by the first parity rule. So 16 by 2 is 8. 8 is an even number, so divide by 2, you get 4. 4 is an even number, so divide by 2, you get 2. 2 is an even number, divided by 2, you get 1. But 1 is an odd number now. So I have to use this particular rule. Multiply 1 by 3 and add 1 to it, you get back 4. So once you reach 4 to 1, it becomes a cycle. You get 4 to 1, 4 to 1. So the last three numbers, wherever you start, will always end with 4 to 1. This is what Collat's conjecture is about. He claimed that for any starting number, natural number, you always end up with 4 to 1. Okay. Now, this conjecture, incidentally, has been proved to be true, probably up to, again, 300 quadrillion places, numbers. Up to 300 quadrillion numbers, it has been proved to be true. No number has been escaped from this, but some numbers, of course, like if you start with 19 has a larger sequence and before ending with 4 to 1. And if you take 27, it takes 111 steps to end with 4 to 1. So for some numbers like 10, you end up with 4 to 1 immediately. For some numbers, it's quite lengthy, but some numbers, like I have listed those numbers, these numbers have more length compared to any of the previous numbers. In that sense, these are record setters for having large cycles in Collat's conjecture problem. Okay. So after 27, the next largest cycle number is 54 and then 73. So if you start with 97, probably it takes more time. It takes more than 100 steps to end with 4 to 1. But you're sure enough to end with 4 to 1. That is what the conjecture says. Okay. So, and this is a more larger picture. As you can see, if you start with this number here, so maybe if I start with 106 here, being even number, dividing by 2, it is 53. 53 means odd number. So 53 times 3 plus 1 is 160. So I come here. 160 is an even number. So divided by 2 is 80. 80 divided by 2 is 40, 20, 10, 5, 16, 8, 4, 2, 1. So I ultimately end up with 1. So it doesn't matter wherever you start, you follow this path here given by this thing, you ultimately end up with this numbers. Okay. And end up with 4 to 1. And after 1, you again go to 4, then it is 2, it is 1, as said by Collat's conjecture. So even after verifying for that many big numbers, people could not show probably that this is so for all numbers. In fact, Paul Addish used to say that mathematics is not yet ready to prove such results. And in fact, this forms a base for what is called dynamical systems, which has very great applications. But it's quite surprising that such a simple rule has created a wonderful result, which keep mathematicians at bay. They cannot prove that beginning with any number, you always end up with 4 to 1, this cycle. I don't know. I mean, in spite of a huge amount of research done by many people throughout the globe. So this is one of the good unsolved problem, and people try to extend this to complex numbers. Now, if you construct this complex function like z by 2, remember, it's a generalization of n by 2. Whenever n is even, it's n by 2, and whenever n is odd, it is 3n plus 1. So extending this to complex numbers, for n by 2, I took z by 2. For 3n plus 1, I took 3z plus 1. And when you multiply by this by cos square pi z by 2, and you multiply for the odd case with sine square pi z by 2, you get this beautiful picture. So this picture is graph of this complex valued function. And you can see this is that portion. Wherever you start, you come to this portion, you come to this portion, you come to this portion, finally you come to this portion. It doesn't matter, wherever you start, you always come to this middle portion. Probably even if you start here, through this line, you can come here. This is a fractal picture resembling this two-dimensional picture here for natural numbers. Okay. Now the next problem that I want to discuss with you is called sunflower conjecture. I dedicate this particular talk to this man whose birthday was day before yesterday. I always admire this great man called Paul Addish, who was well known to research mathematical people because he is the one who has published more than 1,500 research papers, original papers, and of course he lived from the period 1983 to 1996. For 83 years he was alive. He was a very recent mathematician who passed away precisely 25 years ago. So he has been to India on a couple of occasions, or I mean some occasions, not exactly known, but I know that he has been to India several times, and he is a man who was who originated the probabilistic graph theory, who was considered to be king of numbers, and he traveled throughout the globe without he never had a permanent job, he never had anything with him, he never had a home for a shelter. I mean, never cared about worldly possessions. Such a great man. Okay. And this sunflower conjecture was proposed by Paul Adish and Rado, these two people. So this is a real sunflower picture, and they define sunflower conjecture to this idea. You take non-empty sets, maybe how many sets you want you can take. Like I'm taking 3 non-empty sets here, and list out those elements here. So the elements of A are 1, 2, 3, 4. Elements of B are 1, 3, 5, 7. Elements of C are 1, 3, 9, 27. Now this middle portion is the intersection of all the sets, and this middle portion intersection of all the 3 sets. As you can see here, 1 and 3 are common to all the 3 sets. So intersection of all the sets A, B, C will be 1, 3. They defined this common intersection portion as kernel of just like kernel of a homomorphism or something in a group theory or in algebra. This is kernel for the sunflower. So this the remaining elements are resembling the petals of a sunflower. Okay, they are the petals of sunflower. This is called the kernel, the common intersection portion. And for this particular 5 sets, and you can see the length of the petals may differ. That is what actually you see in a real sunflower. Actually, the length of the petal may not be same. For some flowers it might be same like this, but for generally it may not be the same. So keeping this in mind, they had given this particular name called sunflower. Now, what is about this conjecture? They published a theorem in 1960. If you have at least this many sets, w factorial into r minus 1 to the power w sets, each with maximum of w numbers, then there must be a sunflower with r petals. So this number of sets will guarantee you to get a sunflower with r petals. Okay. Now what they suggested is, they thought that this number of sets is very huge, because w factorial becomes huge when w is large, isn't it? Factorials grow very, very high as you take numbers. I mean, it's a very quickly diverging factor. Okay, so w factorial increases rapidly more than compared to any other proper polynomial function, and therefore they thought that you can find a constant c for which this margin, this bound of number of sets, can be reduced to the term c power w. And recently, there were many people who have been working down to find the constant c, so that this upper bound margin of sets proposed by Adish and Rado could be reduced to this form. Now, a recent paper, and now here this example is quite interesting. People might think that you may take sets where there is no intersection at all. So this is a mathematical sunflower, not a real sunflower. A real sunflower may not be looking like this, because you need some portion here to hold all the petals, isn't it? The middle portion. In a real sunflower, you need this portion to hold all the petals together, but in mathematical sunflower it may not be the case. You may not find the intersection portion at all. If the sets are disjoint sets like this, this is a mathematical sunflower. In that sense, the sunflower defined by these two people were more general than compared to the usual sunflower that you see in nature. Okay. Now, several people suggested different bounds, but the recent beautiful, after this, there was not much work. Of course, the one work came in 1997, 37 years after this conjecture was proposed, but that was not a very drastic improvement. But the recent work by this people, this 4 authors, which was published in year 2020, very recently, exactly a year back, 1 year back, they suggested that c can be log w. See, the rate of log w is very slow compared to w factorial. Okay, so people who know analysis very well know that log n diverges to infinity very, very slow compared to n, and n is very small compared to n factorial. So this factor is what they suggested. As you can see in the abstract, they could have written here, they proposed that the c can be taken as log w. So even this goes to infinity when w is large, but the rate at which this factor going to infinity, diverging to infinity, is much, much smaller than this. So this is practically useful for considering or constructing a sunflower with R petals. So this is a very good proof, and you can find this paper in this link. It is available for free download. So wherever possible, I'm giving the sources to you and the paper itself for your convenience and understanding. The next problem that I will be discussing is called kissing number problem. Don't take in the wrong sense. This is touching, kissing in the sense touching of objects. Okay. Now, there are two possible circles here. How many points that they can touch when we take two objects like this? If I take a rod and take another rod, they touch at one point. This is in one-dimensional case. So circle is in two dimension, but if I take two rods or small strings with negligible thickness, they touch at one point like this. So one point of intersection for one dimension. For two dimension, if you take a circle, of course you have to take objects with same radius, same size rather, okay, not different sizes. Okay, if you take a circle in two dimension, how many maximum circles that can touch this particular circle? As I said, the circles constructed that you take should be of same size as for the given circle. So for the given circle in two dimension, you can have maximum 6 possible circles touching it. This is the maximum possible case. Okay, this is in two dimension. Now Kepler, some 3 to 4 centuries ago, made a conjecture in three dimension that this number is for two dimension 6 is called the kissing number for circle in two dimension, and one is a kissing number touching. Kissing means touching here for one dimension. So for one dimension, the kissing number is 1 because only one point, two objects in one dimension can touch, and maximum point of intersection that equal objects can touch a given object like circle is 6 here. As you can see, the hexagonal arrangement here. So probably this is why honeybees look like hexagonal shape. Nature is the best optimizer, and it knows how to best optimize itself by constructing the best possible shapes that mathematics could predict. So that's a wonderful thing to see actually. Nature always choose the best thing. Okay. Now in three-dimensional, if you take spheres, how many maximum possible spheres that can touch a given sphere? The red sphere inside. Possibly the other spheres which are in backside of this picture, unless you rotate it, it's not visible. Unfortunately, this is a static picture, not a rotating dynamic picture, and therefore, but I can tell you that the answer is 12. But this was actually conjectured by Kepler. Kepler suggested that there are 12 maximum spheres that can touch a given sphere, but people were working very hard for it, and including Newton tried it, but it went in vain. Very recently, around 1998, Thomas Hales from America proved that there are, in fact, 12 spheres. And of course, he used a computer-aided proof for this, just like four-color problem was put. Four-color conjecture, and a very famous problem in graph theory, was proved by using computers. Similarly, Thomas Hales used computer-aided proof to prove that there are indeed 12 spheres which can touch as a maximum sphere. So the kissing number in three-dimensional is 12. Now these are the bounds. Now people in 4-dimension using Leech lattice, which exists in 24 dimensions, they proved that in 4-dimension there are maximum 24 intersections that one can make. In if you take a sphere in 4-dimension, for example, 24 spheres can be accommodated surrounding it. That forms actually a lattice called Leech lattice, and it exists in 24 dimensions. So they proved that there are 24 maximum possible spheres that can touch an object in 4-dimension. But we know the answer even for 8-dimension. For 8-dimension, there are 240 maximum spheres that can touch, and for 24 dimensions, again for 24 up to 24 dimensions, we know is 1,96,560 objects can touch. This is an enormous number, isn't it? Nearly 2 lakhs here. So this people had been working on, but for the other cases, apart from this cases like 1-dimension, 2-dimension, 3-dimension, 4-dimension, 8-dimension, and 24 dimensions, the other cases is yet to get resolved, but they had proved some lower bounds and upper bound. In 5-dimension, the kissing number is somewhere between 40 and 44. It cannot be less than 40 and more than 44. In 6-dimension, it cannot be less than 72 and more than 78. So these are all lower bounds and upper bounds, and you can see the work of this in published in AMS, Notices of American Mathematical Society, in this paper, a very good article written about this kissing number. And the next problem that I want to tell you is about unknotting problem. I mean, theory of knots has been a very uh, study of great importance in recent years, and it has direct connections with mathematical biology as well as in dynamical systems, where people try to interact how molecules in chemical kinetics interact with one another. Just it is wonder that how our ancient people used to very casually do all this tying and untying things like knotting and unknotting, what mathematicians call it. Uh, so these things were done effortlessly by our elders, but it was studied mathematically in recent years. It's not a very ancient topic like number theory or geometry. Uh, it has been emerged only a few, maybe a century back or so. But people have been studying the main problem in knotting theory or knot theory of knots is that if you these are all possible types of knots, we want to know whether a given type of knot can be unknotted. That is, it can have so many knots in it, whether it is possible to unknot it and make it like this, like a circle or something where it has no knot. Any unknotted object is, I mean, if there are no knots, it is called an unknot here, like this, a simple knot. Okay, this has two knots here, one is here and other one is here. These are all types of knots which has direct connection to algebraic varieties in group theory. And the main problem is to identify the types of knots. I mean, which type of knots are equal to one another, and among those three knots, which I can unknot and keep it to simple like this, which I can unknot and bring it to like this form. Maybe the answer is very difficult unless you know how to identify it in terms of knot theory. And there was a big idea given by Jones, and it's called Jones polynomial. There's a polynomial called Jones polynomial, which is helpful to identify when a knot can be identified. And there are many theorems that establishes isomorphism between two types of knot, which says that whether these two knots can be unknotted to the same position, or these two knots are isomorphic to each other, or something like that. Like how we study isomorphism between groups or rings or fields, you have isomorphism between two knots. Okay, so one classic example is this. This is the two-dimensional version of this three-dimensional knot. So if I take this first knot given in picture A, I can move it smoothly. I can just pull it away so that it becomes an unknot. Now the second type is this one. This is the third picture. This knot is from the second knot here. What I can do is, this is a possible operation. In making this operation to become unknot, you are not supposed to cut the object. I mean, if this is a rope, for example, you are not supposed to cut the rope, but you can pull it, you can untie it, you can push it here, you can pull it, you can translate it, you can rotate it, you can do something like that, but you're not supposed to cut the object. So that operation is not possible. But you can overturn it, you can rotate it, of course. So what I'm going to do is, in the first case is the knot lying above here is interchanged to below, and below is interchanged to above, so that this orientation is same as this orientation. This part is above here, this part is above, therefore you can pull it like this, and then you can twist it to make it unknotted. So geometrically, because this position as well as this position can be reduced to unknot, I can say that these two knots are isomorphic because they both can be resolved to unknot form. So this kind of, what kind of operations are allowed, and I mean, what kind of, you can associate a polynomial to identify two particular knots and classify them. These ideas are available in knot theory. There are many good literature and many good books available on theory of knots. I would advise those who are interested, and this site is also a very good site for knowing more about knots, and it contains more beautiful pictures about knots. So those who are interested can go and look at this. Okay. The next thing that I want to tell you is about moving sofa problem. I mean, usually I mean, it's not only confined to sofa, but a cot like this where we usually take rest, and any object, a table, for example, when we are shifting a home or our residence, we probably get some difficulty usually in removing this bureaus and cot and other big things, especially because the gateway, the hallway is rectangular shape like this. Okay, so it turns like this, short turn like this, usually the hallway. So this Moser in 1966 ask this question: what is the shape or largest area in the plane that can be moved around a right angle? So we wanted to identify the shape on the objects which can slide easily without difficulty, such that it has maximum area. Supposing if I take a square of unit length, just for example, you can translate it like this. This is a translation. Push it here, you can slide it here, and once it comes to this particular corner, you can push it down. So you can do this operation here in moving from one room to another room, or pull it out from the residence. Okay, if your object is a square, but unfortunately this has area of only 1, because I'm taking a square of side length 1, so its area is 1. Okay, now people are working to find an object of maximum area. As I told you, supposing if you take a semicircle of radius 1, for example, see, a circle of radius 1 has area pi, because pi r square, r is 1 here. Because it is a semicircle of radius 1, the area is pi by 2. A semicircle can be moved here, it can be tilted once it comes to this position, and then it can be slided down. So this area is pi by 2 here. So people had no idea about what could be the best possible shape, and pi by 2 is approximately 1.57, because pi is 3.14 approximately, and this 1.57 number is more than 1 in square shape. So the semicircle shape when you of the object is much better, because it gives an area of which is 0.57, greater than the square shaped portion. This area is just 1, but this area is 0.57. 1.57, which is 0.57 more than the first case. But no one is sure what kind of best possible shape is this. People are working through computers to design several objects here. Now this man in 1968, 2 years after Moser posed this problem, constructed this object. This object consists of shape like you get a rectangle in the middle here, and you cut a semicircle here. This radius is between 0 to 1. He said that the radius can be any number between 0 to 1. And this is another big circle. This is portion of a circle cut into half, and then choose a radius between 0 to 1 and cut this semicircle. This probably looks like more of a, this is a straight line segment. So you have to, not a circle here. This is a straight line segment here. So put a rectangle over here. This probably resembles like a old telephone thing. I mean, handset of a telephone, the older telephone, the landline one. Okay. So resembling that handset of a telephone. Now, if you take this particular object and if you try to move this in the right angle corner, it will have an area of pi by 2 plus 2 by pi. So for the want of time, I'm just giving the expressions. This is the maximum possible area for this shape. It works out to 2.2074 or something. It's not visible for me here. Okay. And then in 1992, Gerver created this shape. This is almost similar to the previous shape, but there's a sharp corner here. The sharp corner was changed to this corner, and the straight line segment, length of the straight line segment was little reduced compared to this segment here. So making some small rearrangements, Gerver could find an object whose area of moving the sofa, this turns out to be 2. How much is this? It's not visible for me here. It is actually a little bit more, comparatively little bit more, not very much. I think it's 2.21 something. So if you work out the difference between these two models here, this area and that area, it turns out to be 0.0121. So approximately only 1.2% difference between the model proposed by Hammersley as well as Gerver. But still it is a very good improvement, and no one so far has found any good shape which has more area than this particular shape proposed by Gerver. In fact, this was recently proved in the year 1992 by Gerver in this Springer paper on moving a sofa around a corner. This is again available in the, not available, it's a paid paper. So the abstract I had given here, so I could not get the whole paper. It's not free access paper here. Now, the other mathematicians were trying to create a possible shape with not just one corner, right angle corner, but what happened to the shape when there are two right angles. That is, the object should turn right here and then to the left. If there are two turnings, to the right here and to the left, there are two possible turnings. What could be the shape with maximum possible area to slide down to these two right angle corners? It turns out that this mathematician, Dan Romick, did a great work. I mean, keeping with this. So he worked out many shapes and ultimately ended up with this particular shape. This is a very curious shape that he found. This was very recently done in April 2016. He showed that area of this particular shape turns out to be sum of two values, namely x plus tan inverse y, where x is root of this equation, real root of this equation, and y is root of this particular equation. It turns out that x is this number, and tan inverse y is this particular number. When you add these two, you get approximately 1.6449, 1.65, 645 rather, approximately, and no one could do better than this. And people, I mean, we are not sure whether you can improve upon this, so this still remains as an open problem. So the best possible shape that we have found so far is this, but no one is sure whether you can improve upon it. People are still working on this very curiously. And Riemann hypothesis is considered to be the holy grail of all mathematics. Any active working mathematician as of today would dream to solve this particular problem. This is a problem from complex analysis. And if you take zeta function proposed by Euler, this function, zeta function proposed by Euler, is sum of reciprocals of the nth power of reciprocals of natural numbers, like 1 power s, 1 by 1 power s plus 1 by 2 power s plus 1 by 3 power s, and so on. So this is called zeta function. When you take s to be real numbers, it's called the Euler zeta function. Whereas if you Riemann refined it by taking s to complex number of the form sigma plus it, or alpha plus I beta, however you call it. When s is a complex number, it's called Riemann zeta function. And he said that all the non-trivial trivial zeros are known to be the ones which are negative even integers, like -2, -4, -6, -8. These are all trivial zeros of this, the points where this function becomes zero. And then what Riemann suggested, to everyone's surprise, in a paper in 1859 was this actually. He said that all the non-trivial zeros, apart from this zeros, will lie on the critical line. This strip is called critical strip between 0 and 1, and this particular line where the zeros of the zeta function lies is called critical line. There's no one who could find any zero beyond this critical line, either to the left of it or to the right of it. So far no one has found it, as well as no one could prove either that all the zeros of zeta function lie on the critical line. Okay, so this was still an unsolved problem. This was considered to be the most difficult as well as the best unsolved problem that exists in all of mathematics today, named after Riemann. I mean, Riemann was a genius of all mathematicians. And recently, in April of last year, people were trying to verify this Riemann hypothesis for as many numbers as possible. And this man, Dave Platt, had written a paper. Okay, this was available in the internet. You can just type this, you can get it. The Riemann hypothesis is true up to 3 trillion places. So though we know that this result is true for, which means up to 3 trillion zeros that has been discovered for the non-trivial zero that we discovered for zeta function, all the non-trivial zeros up to 3 trillion zeros all lie as predicted by Riemann, all lie in the critical line. That means they have real part half, imaginary part some particular numbers. Interestingly, they all lie in the straight line whose real part is half. So this straight line has an equation of half plus it for some t. The real part of this line is half, imaginary part is some number. So it's a beautiful alignment. And the most important thing that makes Riemann hypothesis very special is because most of the hundreds of results depends on the truth of Riemann hypothesis. In other words, if someone could prove Riemann hypothesis, then they eventually can prove all the rest of the theorems which depend on this important theorem. That is first important thing. The second important thing about Riemann hypothesis is that it answers the distribution of primes. So once Riemann hypothesis has been proved, we know how primes are distributed in the number line. So with these two aspects, Riemann hypothesis is said to be so important, considered to be the most wanted problem, unsolved problem in mathematics. Any mathematician would dream of proving this. So, and there was some list of 7 problems made by Clay Mathematical Institute recently in 2000. 2000, in fact, was the year 2000 was declared as World Mathematical Year. And in that year, Clay Mathematical Institute organized 7 problems, unsolved problems, in which one has been solved in the year 2003 by Grigori Perelman. That's a special. I mean, you can allot a special session for talking about Grigori Perelman's achievement and life. Is a very important mathematician who not only proved Poincare conjecture but rejected the price offered for solving all this problem, because each of the 7 problems, according to Clay Mathematical Institute, has price money of 1 million US dollars, apart from other prices and benefits that you get. In fact, not only Perelman rejected the 1 million US dollars for proving Poincare conjecture, but he also rejected the prize money from Mathematical Union, IMU, International Mathematical Union, as well as he rejected the Fields Medal, which was offered to him uh, in the year 2006 in the ICM, which was conducted immediately after getting this proof. This theorem was proved in the year 2004, finally accepted. But he told that equal credit should be given to American mathematician Richard Hamilton, because I was using his result also in proving this. It's one of very deep theorem proved by this man. So if you find such a person who could reject every price, because he told that mathematics to me is important, not just prices. So the claim is important, but we are not working for prices or money or fame or something. So that kind of mathematician is very, very rare to see in this type of materialistic world. The other problems, there are 7 problems in which one has been proved in Millennium Problem. The other 6 problems are P versus NP. I'll give a short, quick notice to decide whether a problem is solvable in finite, I mean, in short time or not. That answers is P versus NP, polynomial versus non-polynomial time. Hodge conjecture is about um, surfaces, I mean, joining of surfaces, and answering about how surfaces can be glued together to form an object of in higher dimension. Riemann hypothesis, I said just now. Riemann hypothesis, one of the Millennium Problems. Yang-Mills existence, and this is about particle physics, and it talks about how particles interact, and they talk about a concept called mass gap, which is very deep actually. So you can, there's a good book on Millennium Problem describing all this problem very briefly by Keith Devlin. So those who can afford to go, it's a very small book but very good book by Keith Devlin. You can refer that book to understand very clearly about all this problem. Navier-Stokes equation is one of good problem because it explains how airplanes, the boat traveling in it is concerned with fluid dynamics, how the turbulence is created, how when a boat travels very quickly in sea water, how the waves travel, and the behavior of such waves and air turbulence has been discussed very deeply by some differential equations in Navier. The Stokes, of course, is the name Stokes is very familiar because he's the one who gave the Stokes theorem in vector calculus, is that particular man. And Birch and Spinetta and Dyer conjecture is again a deep conjecture about elliptic curves and number theory and other things, which shows that there are some, though by Hilbert's 10th problem says that there is no shortcut procedure or methodical procedure that can be available for solving any given problem. But this people said that there are such procedure for special type of problem which are connected to elliptic curves and other special classes of algebraic varieties. And that conjecture has not been proved so far. So these are all this, and you can use this link to know about this Millennium Problem in CMI website, Clay Mathematical Institute website. And each problem carries 1 million US dollars, except Poincare conjecture. The rest 6 are unproved. So if you can prove one of this, you not only become world fame, but you can claim that 1 million US dollars price, apart from Beale's conjecture that I told you. So probably what before I finish this talk, I used to tell young teachers that you create some passion and interest with you. Don't start with a very big problem. See, all this problem that I mentioned now are very classical. They're very difficult because this has resisted so many great minds so far, and otherwise it could have been proven by other mathematicians, isn't it? They could not have come across this many decades or this many centuries or even millennium until they get solved. So they are not so easy problems, but there are always scope for us to start with elementary problem and then work on it, do some active research on it, and then try to solve this. I mean, if you take any great mathematician like Terence Stowe or other people, they do some research in a basic level first, and then they concentrate on big problem using the basic things that they have done. So this is just this collection again is not an exhaustive collection. These are my favorite problem that I like most in unsolved problem. Most often I used to present only in pictures so that people may get some feeling about what we are saying rather than writing down so many formulas and steps mathematically, which creates some kind of uneasiness to them. So pictures, conveying facts to pictures is one of best method that I like most. So what little I know, I had presented to you. It is up to you to choose simple from those who wish to do research. Choose problems according to what you like, choose simple of them, and then create some basic ideas in it. Finish your research first and then try to uh, resolve this kind of difficult problem. If you come up well, it's well and good, you attain world fame. Even if you are not, you can very often find out some other idea so that you can make some good papers on it. So doing research itself is a big experience, it's an enriching experience. With that, this I can complete my talk. I thank everyone for supporting and giving this opportunity to present what little I know before you. Thank you.